Hello to everyone, and thanks for listening in to my online APS talk. I'm really grateful to have the opportunity to talk to our community about my research despite the cancellation of March meeting. My name's Claire Edmunds. I'm a PhD student at the University of Sydney in Australia, working in trapped ion quantum devices. With our team, I've been working to measure and characterise the effect of noise on quantum experiments, as well as develop error-robust quantum control techniques. In our work, we're using ytterbium-171 ions, which we confine in a blade-style linear pull trap, shown here on the screen. We can encode a qubit in the ground state hyperfine manifold, which is split by about 12 GHz and has first-order insensitivity to magnetic field fluctuations. We perform state detection using state-selective fluorescence when we shine a laser on it to excite the 1 or bright qubit state, highlighted here in yellow. To manipulate our qubit and perform single qubit rotations, we use a microwave field at 12 GHz, generated from a keysight vector signal generator. Now, I just want to draw your attention to this loop here in the diagram of our ion trap. This is an in-vacuum microwave antenna, allowing us to deliver the microwaves from a position close to the ions in order to manipulate the qubit state with the strongest possible power. Using this setup, we achieve a single qubit randomized benchmarking error rate of 2 times 10 to the minus 5 when we have a single ion in the trap manipulated by microwaves. But what if we consider more ions as we add more and more ions into the trap to scale up our quantum device? Well, we can still use our microwave field, but now we're going to be driving global simultaneous rotations across the string. We cannot perform individually addressed gates as the microwave wavelength is much longer than the string of ions, so we can't straightforwardly focus it down to hit just one ion like we could a laser beam. Nonetheless, we'd like to do any multi-qubit global rotations in our simulations or algorithms using microwaves, because our microwave gate fidelity is significantly higher than our laser-based gate fidelity. And it's here that we face a problem. Our microwave amplitude is not homogeneous across our qubit string due to internal reflections within the trap, and therefore we cannot calibrate the field for the entire qubit string simultaneously. It's crucial to calibrate the frequency and the amplitude of the field, but it cannot be done for all the ions. The inhomogeneity problem has recently been mentioned in other work, such as a QCCD surface trap, as a limit to performing logical global operations using microwaves. In our experiment, when we run randomized benchmarking using global microwave gates on 10 ions simultaneously, we find that the randomized benchmarking error rates vary by over an order of magnitude. Here, we can only calibrate the amplitude and frequency of our control field for one qubit, and we choose this to be the leftmost one, called our calibration qubit. Indeed, when we measured our randomized benchmarking sequences, this particular qubit has an error rate quite similar to that for a single ion in the trap. But as we move away from that ion spatially, the error rates get worse by over a factor of 10. So now what can we do about this? Well, we could move to focused laser-based gates for our global rotations, knowing that despite the increased laser error rate, we could at least have homogeneous qubit errors. However, one would need to measure each ion's parameters individually, creating some sort of lookup table that you can refer to and requiring extensive calibration overhead, which is undesirable. So instead, we turn to an idea out of NMR literature. We use something called a dynamically corrected gate. These are composite pulse sequences created by phase, amplitude, or frequency modulation, designed to create the target qubit rotation with an added robustness to noise in comparison to primitive gates, which are what we call the straightforward, unmodulated rotation. Now, these gates are known to suppress single qubit error magnitudes induced by low frequency noise or static calibration errors. Here I've demonstrated this by engineering noise on a single qubit and using 5 different gate constructions. Performing 10 pi rotations, we scan either the pulse length to induce an over-rotation error or the qubit detuning to induce an off-resonance error. In both cases, a higher measurement on these graphs corresponds to a larger sequence error. The primitive gate has minimal robustness in both quadratures. Two DCGs called corpse and BB1 are single quadrature suppressing, so they can either suppress the off resonance or the over rotation errors. The gates C and BB and the optimized Q control pulse can suppress errors in both quadratures, shown by their robust flat results across a large error regime. So this is great. We can apply these DCGs to suppress our multi-qubit calibration errors. So let's return to our randomized benchmarking results. Here, I've repeated our 10-ion randomized benchmarking using the DCG BB1, which is designed to suppress over-rotation errors and hence targets the gradient in our microwave field intensity. Indeed, we find that the error rates over the string are considerably more consistent than when we use the primitive rotations. Now, the first 1 or 2 qubit error rates are worse than they were for the primitive, but this isn't surprising. They had very little over-rotation error as they were quite well calibrated, and hence the BB1 did little to improve their performance. And in fact, the extended length of the BB1 pulse has worsened the net error rate by making it more sensitive to high-frequency noise. However, the increase is not too dramatic, and we see a significant improvement for all other ions in the string, suggesting that this is a feasible way to proceed with our global gate implementation using microwaves. Now, DCGs actually have several other advantages that I wanted to highlight. It's really important to have the amplitude of our microwaves well calibrated for our experiment. However, for us, the power can drift considerably over time due to thermal fluctuations, which can affect our microwave amplifier gain. As a result, we have to recalibrate our amplitude regularly, a procedure that takes quite some time and quite some overhead. To illustrate this, I've taken a single trapped ion qubit, prepared it in 0, and applied 101 pi-on-2 rotations about the x-axis, which should give a final Z projection of 0.5. Now that you can see that for the primitive gates, our rotations start correctly. We're at about 0.5 when we measure our qubit. However, as we let this procedure continue over time without recalibrating, slowly the gain of our microwave amplifier is changing, and so we're getting an error in our sequence. And over 8 hours, we're actually getting about a 40% error without recalibration. On the other hand, when I look at the BB1 gates, which were done interleaved with the primitive such that they had the same conditions, we see that they're much more robust to any temporal drifts and require significantly fewer recalibrations. Now, I will quickly point out that although the BB1 gate results are more consistent, they are overall correct, sitting at 0.6. This was just due to a human-induced error when I calculated the BB1 gate parameters such that they didn't do quite a pi-on-2 rotation. And we've since demonstrated that the correct rotation can be straightforwardly generated. Now, I'll just finish by flashing up a more subtle benefit of DCGs. This is previous work that we've done looking at extracting the strength of correlated errors within a quantum circuit, using only the final projected measurements and not probing within the circuit. We found that using the standard randomized benchmarking protocol with no modification, one could post-process the results to find this measure of error correlations. Very briefly, we found that the results are hidden in the statistical properties of the errors and the way that that changes how a distribution over sequence fidelities changes with averaging. If the errors are high frequency, incoherent, or uncorrelated in nature, the distributions continue to narrow with averaging, producing 1 on n-like trends when you plot the variance of the distribution over the number of noise averages. On the other hand, correlated errors result in a rapidly saturating and analytically calculable value as the results become dominated by differences in the intrinsic sequence structure, which can't be averaged away over the background noise process. What I'm actually showing here is evidence that dynamically corrected gates actually whiten errors relative to the input noise spectrum. I've engineered frequency noise with both correlated and uncorrelated components, and then I've performed randomized benchmarking with primitive gates and with 2 different DCGs, WAMF and corpse. With the primitive gates, the variance quickly saturates, showing that we remain dominated by the correlated component of the error, whereas under the identical noise, the DCG scale is approximately 1 on n, showing that they're largely undergoing uncorrelated errors. Quantitative analysis has showed a 50 times reduction in the correlated error strength with these results. Now, I just want to finish with another ongoing project to improve our microwave gate fidelities. In addition to control techniques like DCGs, we can also look at improving the purity of our microwave control field source. Currently, we use an IQ modulated key site vector signal generator, which is locked to a 10 MHz reference generated by a rubidium atomic source. One of the problems we face in our experiment is phase noise. Phase noise increases multiplicatively with frequency, which means that despite having a stable and clean reference at 10 MHz, by the time it's converted up to 12 GHz for our control field, we've added 60 dB of phase noise. The ideal way to improve this would be to have a higher frequency reference source. So we started collaborating with a company in Adelaide, Australia, building cryogenic sapphire oscillators, or CSOs. Using a CSO from CryoClock, we can create a high frequency reference at 10 GHz with ultra low phase noise. The CSO actually outputs low phase noise references at multiple frequencies, including 10.5 GHz, which we use for our microwave baseband, and 5.8 GHz, which we will use for the sample clock reference for an ultra low phase noise arbitrary waveform generator. This will be used to create a 1 to 2 GHz ARB waveform with total phase control that can modulate the 10 GHz baseband and create a high purity, phase controlled microwave source, which we can use in our experiments. This work is ongoing, but we can already compare a measured phase noise spectrum at 12 GHz when using the CSO and ARB waveform with a datasheet from our current VSG. Here we see a 100,000 times phase noise reduction on slow timescales at a couple of hertz from the carrier, and a 5 times reduction at frequencies commensurate with our Rabi rate, approximately 1 to 5 kHz from our carrier. We care about noise on different timescales for different reasons. Noise at our Rabi rate scrambles the phase in a single gate and affects its performance. Slow noise will affect long circuits either consisting of many driven gates or idle periods like a Ramsey experiment, because the phase of the gates relative to one another will become scrambled. Individual gate performance may look good, but the performance of the circuit as a whole is now degraded. Considering the significant improvements in the phase noise spectra and predictions from previous theory work in our group, we expect to see improvements in our microwave gate fidelities when we utilise the CSO synthesis chain. This work has been looking to improve single and global qubit gate fidelities via 2 separate pathways. Firstly, we demonstrated that dynamically corrected gates can be used to not just reduce net error rates, but also homogenize error rates in time and space, and reduce spatially and temporally correlated errors. Secondly, we explored the use of a microwave synthesis chain using a cryogenic sapphire oscillator in order to produce a low phase noise control field. Thank you so much for listening in. Feel free to ask any questions that you may have in the discussion here. I'll try to respond as soon as I can.